Thank you for the talk. So Youhui is here to answer questions. Youhui, maybe show your video too. Yeah, so we have a question from Xudong.
Oh, yeah, okay. So great talk, great work. And you mentioned that some selective compression and partitioning mechanism in the talk. So could you elaborate more about like how this mechanism decides whether to compress each gradients or partition some large gradients?
Thanks. Could you hear me?
Yes.
Youhui, we can hear you but not seeing you. If you want to show your video, that would be great.
I cannot open my video.
Then it's okay. We can hear you clearly.
Okay, thank you. As the selective compression and the partition mechanism, we use a cost model to evaluate we use a cost model to design each gradient will be compressed or partitioned.
So the cost model is about like how much cost it will affect the performance if you like try to compress this gradient. Is that correct?
Yeah. The cost model is has two parts. One is before compression. The cost comes from communication and meaning from the communication. And the second part is with compression. The cost model with compression. The cost comes from the communication and computation cost. We compared these two parts and to decision how to partition or compress. Yeah.
Okay. Thank you.
Thanks.
Okay, so our next question is from Chen.
Oh yeah. Can you see me?
Yes.
Okay, yeah, thank you. Great work. I have some questions. First is about the synchronization, that's coordinate synchronization. It seems it's like a centralized asynchronization protocol. So will this one become a bottleneck for the everything? And I feel like you need to monitor the usage, like the data link, that kind of thing. How about the overhead of this synchronization?
Thank you. This is a good question. Okay, I can use my video. Yeah. The bottleneck is let me think. Sorry. Could you please repeat your question again?
Oh yeah. For the coordinated synchronization, that schedulers thing, something like that, will this coordination be, will this synchronization become a bottleneck for the system?
Okay. Answer. The coordination, we use a global coordinator in our design and implementation, but the coordinator, we only send and receive the metadata of gradient, like send to which node or gradient size, like this metadata. This is small, and in our implementation, the synchron coordination phase and the communication and computation phase are top-lined. So, for example, you can, when the communication is running, the coordination of the next mini batch would be launched.
Yeah, so it is the synchronization, the selection of the data link, that kind of thing will be calculated before like each that's like the gradient backpropagation, right?
Yeah.
Only the metadata we use, so will be calculated beforehand, and then the communication will happen.
The metadata is transmitted, and the coordination cost and the communication, the gradient communication cost can be overlapped.
Okay, I see. Yeah, and the second one is for the library, and I'm just wondering how easy it is for the general deep learning users to use to incorporate in their training script. How much changes they will need to make?
This is a good question. We provide a C-like domain-specific language, and the users can use this like DSL to describe their logic of their algorithm. And we implement a toolkit. They provide a ramper to translate the optimize the implementation into the DN systems and register and integrate them into the communication libraries. So we provide example in our GitLab README examples, open source link. Just use the one line command to translate the code. Yeah.
Okay, I see. Thank you. I will check the GitLab. Yeah.
Great. Next question is from Le Xu. Do you want to start?
Oh, hi. So great work. Can you elaborate slightly more on how the compression and decompression process is done? Specifically, did you do this algorithm on top of the so do you use customized kernel and run this in parallel with the regular sort of DNN processing, as well as communication libraries such as all reduce? Second, I guess the second question is, if you do run these processes in parallel inside of GPU with all the other processes, does that sort of generate a delay for any all other works that is being done? Not that I'm saying you're not pipelining, because I understand that you're doing everything in the pipeline fashion, but do you think there will be, because the GPU utilization tend to be really high usually during these process, does the compression and decompression operation generate certain delay when the GPU utilization is really high?
Okay, thanks, Xu. We use different queue and different stream on GPU to manage and schedule the different tasks. For example, the compression and decompression are scheduled by a task queue, and the communication is scheduled by another queue. This queue is managed and scheduled by DN system engine. They can run in a synchronously way, and for example, the different computation, like a DN system, a DN model computation, and the decompression and compression computation, they use different streams on GPU to run in a parallel way. I don't understand your second question.
Because they are using different streams, so basically you can actually launch parallel kernel in the system. I'm just wondering. I understand that you can launch parallel kernel in the GPU, but I'm just asking, in your experience, did you observe any delay to the regular process? Because if the GPU utilization is very high, then even if you can launch things in parallel or asynchronously, you're still occupying all the resources in a way. So let's say if you're using large batches, for example, then potentially your utilization is already very high. So I'm just wondering if you're like adding this decompression compression operation inside, would it, how does that affect other kernels that are also running in the system at the same time?
Yeah, this is a good question. The DN model is computation intensive, and the compression algorithm is memory intensive. We find this is this point, and use different stream on GPU to schedule and manage them. So the compression algorithm use the memory bandwidth of GPU. and the DM model computation is usually a course of the GPU. They don't conflict, so we can, and we measure the breaking down evaluation and find only a little delay of the DM model computation, about less 5%.
Okay.
I see.
Thank you.
All right, thank you.
We can discuss this more later. So let's move to the third talk of this session. This talk is presented.
Thank you for the great talk. Do we have questions from the audience? Inho?
Hi, Uni. Thanks for the great work. I'm Ino, and I'm from NUS. I have a question about I think you in your conclusion and in the early stage of your presentation, I think you mentioned about the existing compression algorithms have some like great potential, theoretical potential, and the compression ratio is actually very high, like 90-something%. But in practice, we observe like much lower effect in terms of the performance, like 30-something% reduce of the synchronization ratio. So I'm curious, what is the reason behind that? The main reason behind that? Why we observe that kind of like big gap between the theoretical expectation and the practical result?
Okay. Thank you, Info.
Yeah.
This question is a good question, and in our, let me think. Sorry. Sorry.
Hey, would you mind I take over? I take this question. Okay. Can you hear from me? Oh, okay, it's
I can hear you. Yeah.
Okay. I also co-authored this paper.
Yeah.
Thank you for this question. I think this is a very interesting one. Definitely, there is a trade-off between the computation and the communication in distributed training, right? So the performance of the ratio of the synchronization on the whole pipeline actually affected by many factors. For example, how fast the network should be, and how fast the GPU should be, and also what's the type of the model actually used. For example, the model could be the communication intensive, and some of them may be communication intensive. So for example, in our evaluation, right, we take the ResNet, for example, that is truly computation intensive, which means even with large scale deployment, the synchronization overhead is still not that big. Even though actually for this kind of computation intensive workload, right, our framework HyperS with this compression enabled still can improve the performance. That means when the scale become large, the communication eventually will become the bottleneck, right? Because our assumption is that we use this bulk synchronization, which called like a BSP, right? You always run like distributed barrier, and which means at each iteration you push a lot of data across different machines. Yeah, that is my answer. I don't know whether that satisfy you or not.
Yeah,
Thanks.
it's great answer, but one follow-up question is, you know, for using the existing compression algorithm, we can reduce the size of the gradient like significantly, even more than like 90%. But still, we observe like we cannot get that kind of big advantage in practice, right? In terms of the synchronization, yeah.
Right, exactly. So that's the problem we try to address, right? So you have a computation intense overhead because of the compression. I think the worst thing is that it's actually contradict with the common optimization we put together for this compression unaware training, right? Without the compression, actually, we have a lot of optimization to optimize the network, to optimize this pipeline. But once you compression add into it's actually introduced a lot of unique characteristics, which lead us to rethink how we need to design this pipeline, right? It's how this, what's the motivation for the high press work? Yeah.
Got it. Yeah. Thank you.
Thank you. Thank you for the question. Yeah.
Thank you for the great answer. We have two more questions from the audience. So let's go with Ji Xiong from HKU.
Thank you. Thanks for your great talk, and I think it's very impressive. I'm Shi Xiong from the University of Hong Kong. So an important mechanism in the gradient compression, I think, is the error compensation, because you want to make the gradient lossless. So you should do some compensation to the errors. So my question is, as you have a very powerful language there to program the gradient compression part, so do you think you can support the error compensation part? And another short question is that I think like 1-bit Adam, some optimizer used in deep speed, a very recent and very powerful training system, has already used some gradient compression. Do you have any plan to support this kind of system? Thank you.
Yeah, so thank you, Shi Xiong. For the first question, we provide a C-like specific language, and we this language is extensible, and we can provide to describe more popular algorithms. And for the second question, deep speed is a popular framework. It combines model parallelism and like the CPU swap strategies. In high press, in high press, we only support the data parallel strategy, but we provide to support the model parallel and other model parallel strategies to update our high press.
Thank you. That answers my question. Thank you.
Thank you.
Okay, so the next question from Gao Wei.
Hey, I'm Gao Wei from Nanyang Technological University. I have one question. If I find that there are two key components in your system, sort and filter, and in compression stage. However, for sort operation and the filter operation, sort operation will induce the time variation, and the filter operation will induce the communication tensor size variation. So how to handle this dynamic case? Yeah, this is my question.
Sorry, can you repeat your question?
For compression algorithms like sort, you make top K, and you need to call the sort function. And however, it is not time stable. So this is one case. And for filter, maybe we have a threshold to filter some gradients. This will induce the communication tensor size variation. So if we have static information or the fixed information, we can schedule it very well. But if we handle the dynamic case, it will induce some unexpected system overhead. Maybe sometimes the sort, the time to sort plus the time to communication will large the time to communication sparse tensor communication will be larger than the full tensor communication. So how to handle this case?
Yeah, I understand. In our implementation, the sort and the filter is implemented by the library of Buddha named Thrust. It provides the high-level API like sort or filter or max. So we consider it a good tool to implement our compile. And as you see, the cost of the filter and the sort is high, and so it may delay the synchronization of gradients. So we make a cost model to decide a small gradient with compression or not. Yeah.
Maybe I want to comment a bit if I have time, right? So just short answer. For this time variance thing, so far because we highly optimized the library, we did not observe that, but that's interesting. We would like to follow in future work. And for this space variant, like the size variance, right? That's good. So far, actually, a lot of algorithms they follow use this static compression ratio, right? So you need to select like a 10% or like 1%. That is for sure easy to handle. For this dynamic one, actually another so far actually we're thinking too is that we need to rely on this coordinator to first synchronize this dynamic stuff, and finally to send the and later actually use this coordinated information to guide the scheduling. Yeah, I think that's the current status. But definitely, this variance stuff are very interesting.
Okay, thank you for your explanation.
Thank you.
Thank you. Thank you for the questions and answers. Because of time, we have to go to the next talk. I also have a question, but I ask on the Slack.
Thank you, Gong.
Yeah, thanks.
So thank you.
So the last talk in the session is